Welcome to another video explaining the universe using the particle model. Well, today's video is about the cathode ray tube experiment that originally was done by J.J. Thomson. And we're going to talk about electric field deflection in this video. There's two pictures from this link showing the ray. Right here you can see the ray moving up, bending up, and then here the ray bending down. And it's being bent by two plates inside here that are charged with a DC voltage, and this one is as well. All they did here was to reverse the polarity. Plus would be here, minus here would make it go up, plus down here on this terminal down here, and negative up here makes it go down. The odd thing is these aren't really two different things at all. You could just stand on your head, look at this one, and you have this picture. Physically, what's going on is the same thing. There's no difference between the two. Okay, so here we have electron deflection, and what you have is a equivalent of an electron gun here, with positive on the anode and negative on the cathode, and positive on this plate and negative. In this case, the plates are outside of the tube, just as a drawing. And it states an electron gun with a voltage of 100 volts, 100 volts here and 100 volts there, will have a speed of 6 million meters per second. That's 2% of the speed of light. So this electron ray is not going at the speed of light. The electron is labeled negative because it turns towards the positive plate. This experiment doesn't tell you what the electron is made of. It doesn't tell you why, what physical property it has that makes it go this way. J.J. Thomson concluded that it must be negative since it's moving towards the positive plate. It's labeled that. We define it that way. There's no explanation of the physical property. Secondly, here you have actually two electric fields. You have this electric field that does causes it to bend up, and you have an electric field here. And they don't ever usually talk about this one, but it's there. Oddly enough, if the electron or G1 particle comes flying through here at speed c, this force is going to slow it down. That's not what they say. What they say is it speeds it up. Well, whichever explanation you like, that's clearly up to you. Now you can actually see an example of one bending down, but the only example I found was a helium-4 nucleus. Helium-4 is the most prominent form of helium in our world, and the helium-4 nucleus is actually called an alpha particle. It has a positive charge. 2 protons and 2 neutrons, at least that's the standard explanation. And it's emitted from uranium. Yeah, we have nuclear radiation going on here, which is why you don't see this one all the time. People just don't get a supply of uranium and set this thing up and do this experiment and put it on YouTube. But the alpha particle moving this here has a speed of about 15 meters per second, 5% of the speed of light. Both of them moving relatively slow. But there's an electric field here. In this case, the electric field, again, is from the plus plate to the minus plate, and it's pushing in the same direction. Unfortunately, I didn't mention it, but here you have an electric field pushing down, so to speak, moving down, but the electron moves up. And that's a little bit of a sleight of hand that the standard explanation uses to explain the motion of the electron. Most commonly, it's just negative is attracted to positive. That's the standard. They don't talk too much about the electric field. But in this case, the electric field is in the same direction, so it works properly with a positively charged particle. So I decided to look up electric field at this link, and it stated an electric charge produces an electric field. That's how you get one. You have to have a particle with an electric charge. And that electric field, which is a region of space. The electric field is a region of space. Field is space around that charged particle or an object in which an electrical charge would feel a force. You know, we feel these forces. You know, in outer space, you don't feel space. On the surface of the Earth, you can feel the atmosphere, but there's something physical there. We can feel an electric charge of a balloon on our arm or whatever. You can actually feel there's something there. There's something moving. There's something physical. And yet they say an electric charge produces an electric field, the electric field which is a region of space. It's space. Crazy definition. Okay, so in the cathode ray tube, I showed you had two plates, one for showing the equivalent of electron gun and one doing the deflection. These are air gap capacitors. Well, inside the tube, it's not even an air gap capacitor because they empty the tube of it's a total vacuum. So there's nothing in between the plates. It's not even an air gap. It's a space gap capacitor. Now, when you charge this up with 250 volts DC, the particle model sends G1 particles around, and if it's going to have what I call a charge, it's going to accumulate a lot of G1 particles here. Well, in a vacuum, I don't know how the charge charges up in a vacuum if this is a total vacuum, so it must be the plate. It must be the plate that has this excess of charge, and you need to have it because once it's fully charged, you have to lose the equivalent number of G1s passing through here in order to get the voltage drop. Now, recently, from a recent video I had, there was a pretty wild discussion going on about charge. Now, let me reiterate my final answer to that dialogue. The particle model assumes that the G1 particle has no charge. It's not negative, it's not positive because there's no physical property. So when we say the G1 has no charge, or the G2 or the N1 nucleon has no charge, we're talking about the particle itself. In the case of a capacitor, I do use the word charge, and it has a negative charge when you have an excess of G1s here, and it's a positive charge when you have fewer G1s or even missing G1s on this plate. So an object, not just a particle, but an object, I will use the word charge because that's how we normally talk about this. For me to make up a new word to say this is whatever would be confusing. But so we use charge. I use charge in the sense of charging an object like a balloon, but I claim that the G1 and the G2 and the N1 and N2 do not have charge. Well, once you establish an excess of G1s here and fewer G1s there, you get a force field buildup because the G2 particle is surrounding at this device, coming at it from all directions. You have a lot of loss here, creating a stronger force pushing down. And then the other way, you have a little bit of loss here until you get there, having a smaller force pushing up. Always two competing forces. Because of this imbalance, like the imbalance of the moon and the earth, you get a net force in this direction. And therefore we have what I call a G2 gravity, or F2. F2 is the net force. That's what the blue arrows represent. That force is in the same direction as the electric field. Not a coincidence to me. Okay, so when you deflect, the electrons moving from left to right through this air gap, they move up. And the question is, you got several things going on here. You not only got the G2 force pushing down, but you got G1 particles flowing up, and G1 electron beam throwing through the plates this way. G1's up, G1's through, F2 down. G1 to G1s, when they hit, that's a collision. F2 is G2 gravity. F2 is the net force of G2 gravity. So which one is it? Well, this is my answer. Collision wins. As in most cases, there are two competing forces, collisions of G1 streams and G2 gravity. When magnets repel, the collisions are stronger than the G2 gravity that pushes them together. There's competing forces in gravity that you feel just while you're watching this video. My contention is that these electrons are going to hit, and some of these are going to move up, and some of these, oddly enough, these are going to push these up in the same direction. So some of these, the cathode ray going up, come from here, and some come from here. And F2, which is moving down, obviously isn't effective in this case. These are moving at speed c. I claim these are also moving a very fast speed c, and they're being sustained by G2 gravity as well as it, and so it moves up, and I claim that the effect is the collision in this case is stronger than the F2 force. Okay, now the deflection of the alpha particles. This is just a repeat of what I showed before. In this case, you got the same competition of the alpha particle, but it moves down. Now, the one big difference, the alpha particle is moving faster, if you believe the measurements, than the electrons in the cathode ray. So they're moving faster, but that moving faster should try to make it continue. But on the other hand, the alpha particle is 4 N1 or 4 nucleons. There are 4 nucleons. This is a heavy particle. This is not light. Contend that this G1 force does hit and would cause them to go up. In fact, there may be some that move up, but this is harder to move. This is like a ping pong ball trying to move a bowling ball. Well, maybe not that severe, but because normal gravity is caused by pushing gravity when G1s hit an atom, and this is a nucleus of an atom. So yeah, there's some motion there. But in this case, the F2 force dominates and causes it to go down. The F2 force wins. So the conclusion is the electric field has no physical description, and it moves the electron the wrong way, moves the alpha particle the right way. They claim it's an open space around a charged particle. and yet you can feel the force, the electrostatic type force that comes from the electric field. When a glass rod comes near your arm, and your hair stands on end, you can feel it. You know there's something physical. They give no physical description. TPM has two competing forces, G2 gravity and G1 collision, that provides the type of mechanism needed for moving the electron in one direction and the helium nucleus in the other direction. It all depends on which force wins out. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.